Hi, I'm again back with more switching labs and lectures. So today's lecture is the continuation of the previous one. So hopefully you enjoyed my previous lecture and the video. So that was about the switch, and today we are going to go and talk about the next, which is called a spanning tree, and when we are connecting more than one switches. So what we do is we all know that by this time that the main job of the switch is to do basically forwarding. The messages or the frames comes into the packets, into these different ports, and it announces. That means it broadcasts or it multicasts or it unicast through the ports. So basically the main function of the switch, let's try to figure out what are those. So number one is to forward. So something comes in, it's going to go and forward to the outgoing ports. Now, as we learned earlier, that if a switch knows the MAC addresses of the computers on the network, so then it will be easy, it will be filtering, it will send the messages out to the known ports. If the known ports are unknown, that means it never learned the addresses, the MAC addresses on different ports, so it is going to go send a general broadcast. Now, this is the whole idea of a switch. Now, what we are going to talk today is that if we go and put more than one switch in our network. Now, why we do to put more than one switch here is clearly in a networking, there are two very important fields, the aspects. One is called the fault tolerance, and then is the redundancy. If you have only one switch and that switch goes bad, that means your entire network is down. So what we do is we go and put more than one. Now, the problem is when we are putting more than one switches together, and then we connect them because we want to make a redundant things, extra things. The ways these switches are learning, as I said earlier, switches are all physical MAC addresses. So when a computer is sending a message through switch A, it doesn't know where to send it, so it's going to send a broadcast to every port. So clearly you can see that when the message comes in, is going to this switch 1. Let's say there's a PC, something comes from here, and then it's going to go and let me put it here. So for example, we have a computer, and let's say put it here. And this machine, let's see, we have another computer here. And then we go and connect with the cables. So fast Ethernet here, and let's go and connect with port number 2, and then do the same thing with port number 2 on the other side, for example, or okay, and then whichever port, let's say port number 1. Okay, now, so if we have more than one switches, and when the message comes in, for example, let's say this computer is sending a message to computer 1 on the other side, clearly this switch has no idea where is this in the port set, because if you check the MAC address table to start with, when we remember we learned the MAC address table command last time, show MAC address table. So now I learned 1 and 3. So that means if you are sending a message, it is meant for port 1 or port 3, then it's going to go and send it through 1 and 3. But if some other computer is not in the table here, because you can see there, then it's going to go and send a broadcast. Now, question is, without any control in a more than one switches, like a circular, like physical rule, is a loop. So it will broadcast on this side. It will broadcast on port number 03. It will broadcast on port number 01. When the message goes to switch number 3, it will, again, it doesn't know. It will broadcast on port number 2. It will broadcast back on port number 2 here. It will broadcast on whichever port is connected here. And this, again, this switch will do the same thing on every port. So this is what is called a loop concept. Traditionally, this is a physical law when things are moving in circle. So if you cannot stop it, they go in a loop, like our planet is in a loop. So the very important part here is forwarding and broadcasting and sending the information. What are the few things which are very important? So number one job is of a switch is to listen and learn, because it always takes time. When it's listening, and then is going to go, this is first is learning, and then is going to listen. While it's listening, it is updating its table here. And after it has been done, then it's going to go and forward those packets. So that means it takes time. So we will see the topology which is used traditionally is called 802.1d or spanning tree algorithm, spanning tree protocol, STP. And that STP protocol is known as 802.1d. Now, according to 802.1d, which is from IEEE, main job of that topology or that algorithm is to avoid the loops, to fix the loops. Because once something goes in a loop, you have to shut down the computer, you have to shut down everything. So what we are going to learn today is we are going to go and learn that the algorithm, how does the system is going to help us in avoiding the loops or eliminating the loops. So if you have more than one switch, again, redundancy, 2, 3, 4, 5, keep going. And then whatever traditionally in your different buildings, every floor has a switch, and then you connect them together. So just imagine you have 3 floors, and we are connecting these 3 switches together into each floor. And to start with, they don't know nothing, so they always broadcast. So the switch job is to forward, listen, learn, forward, and then to avoid the loop. And that avoiding the spanning tree, which we say avoiding the loop, the algorithm is known as a spanning tree. And what spanning tree concept is, that by default, we all know that the switch is physical MAC addresses. So what it does, the first rule is that whenever these are switches there, when you put them together, they send BPDUs, bridge data unit. So what they are doing is they are sending the hello packets, by which we call a BPDUs. So bridge data units. And in a bridge data units means every switch says, well, I am the master. Master means the concept is called root. So it announces its bridge ID. That means the identification of every bridge is a bridge ID. And what is the bridge ID? So traditionally, bridge ID used to be, bridge ID is 2 bytes plus 6 bytes of the MAC address. So that means 6 plus 2, 8 bytes. So you can figure out 2 to the power 8 is how much. And then later on, they divided this 2 bytes ID into 2 different numbers. They said these 2 bytes are going to be called 4-bit priority and 12-bit system ID extended. So 4-bit priority means system is going to go and check this one. In the end, we are going to talk which bridge is going to become the root bridge. So traditionally, the first thing is, if the priority is the lowest, because this is a 4-bit number, 0000 to 0001, so 000, that means 4-bit 2 to the power 4, you can figure out 2 to the power 4 is 16. So that means all these switches are going to go and compare their priority, because the MAC is fixed. Every machine has its own MAC address. So now in our Cisco, this 4-bit priority, this is being set. So by default, this priority is called 32768. So let me put it here. By default, in all Catalyst 2960, the 4-bit priority is set as 32678. Okay, so that means by default, the priority of this switch is this, priority of this switch is this, and priority of this switch is this. So that means all of them are having the same priority. So this guy says, I am the root. It sends the BPDU hello. It says, well, I am the root. And then this says, to start with, everyone is the root. Everyone is the master. But once they compare this ID, and this ID is the same on every switch, then there's a tie. So then what system they do, they compare the MAC addresses. So I put that MAC addresses on this one. So every switch has a MAC address. So if priority is the same, remember the rule. First thing is always who's going to become, like in a parliament, who's going to become a prime minister, who has the majority. So similarly, if the priority is the same, because by default priority is set with these four bits and this plus 12 bit system ID, which we call a bridge ID in the end. So priority is the same. So what they do is they go and compare the MAC addresses. So whichever MAC address is the lowest, that bridge becomes the root bridge. Now why I'm saying bridge, because we used to call these switches bridges. Bridges were all software, switches are all hardware. So just imagine before 90s everything was a bridge. Now after 90 now we are using all switches. Rules are exactly the same thing. So if you look on this, so every switch has a MAC ID. So whichever my MAC ID is smaller, that is going to go and become the root bridge. So that means done. So when it's done, only the root bridge is going to go and send the BPDUs, hello packets. The others are going to go and listen and follow. Okay, so now once this becomes the root bridge, every port on a root bridge is a forwarding state. So that means if you are on a root bridge, your every port is in a forwarding state. So that means you message comes in, you forward it. You comes in, you forward it on every port. So right now you can see that this port is forwarding, this port is being forwarding. That's why you're seeing these green thing. Now remaining two bridges are switches, because only one has to be a root bridge per VLAN or per network. According to 802.1d, which is IEEE, one VLAN per network. But we will see that later on. In the Cisco, they have done PVST, the same thing, but they say they are going to have these SPT algorithm running per VLAN, whereas the IEEE says only one for the whole instance, one bridge for the whole. But Cisco says, no, we are going to go and look into different VLAN. So if you have 3 VLAN, 4 VLAN, and 5 VLAN, so every VLAN is a broadcast area. So that's say for every VLAN, there may be a different instance of a spanning tree. Okay, but first let's solve the first problem. So one of these bridges becomes the root bridge. And which bridge becomes the root bridge? First, as I said earlier, they compare the bridge ID, which is by default 32678. And if there's a tie, so then what they do is they go with the MAC address. And whichever MAC address is smaller or lowest, they will make that machine a root bridge. So once it has a root bridge, all the ports on this one are in a forwarding state. They are forwarding. Now into remaining two now, what they are going to do is every other switch, which is not a root bridge, is going to go and decide on root port. Now root port concept is they are going to go and have access to the root bridge. To go and have access to the root bridge, they are going to go and find the shortest path, or according to the cost, the lowest cost. So for example, now we have these two, switch 3 and switch 2, for example. So let me see which one is a root bridge first. So if you go there and if you say enable, what is that? And then once we are there, we go show spanning tree. You just press the tab. So you can see that if you look into this page, system says VLAN 1, because remember I told you earlier, every interface is by default is in VLAN 1. So its priority is root bridge priority is 32,769. I will tell you why it is 69. Address is this. So that means this is the lowest MAC address among these three. And I put there, so you can see that this address is server 3, B011. So this becomes the root. Now what it does, even here you can see this bridge is the root. So what it does, it is going to send the hello messages after every 2 seconds. It is going to inform whatever is going around on the network after every 2 seconds. And then the other guys are going to listen up to 20 seconds. That means they are going to wait. If they are not listening any message by 20 seconds, they will try to elect somebody else as a root bridge. And the bridge priority is 32,768. According to this rule, which I said here, 2 bytes plus is equal to 4 bits and plus 12 bits. This one means. So this is the priority average plus VLAN 1, because this switch right now is in VLAN 1. So 32,768 plus 1, which we call system ID, and now the whole thing becomes the priority. So your bridge ID is based on the priority plus the system ID. We call it extended system ID. That means if you have VLAN 10, so what will be the bridge ID? This is the exam 100% question. What is the bridge ID of a switch whose priority is 32768? So you are going to add 32768 plus 10. So you are saying 32779. Similarly, you keep on adding the VLAN ID into your priority. That becomes the bridge ID. And what is the bridge ID here is? It is sending hello timer after every 2 seconds. Everyone is going to wait up to, that means 20 seconds is 2 times 10 seconds. So that means they are going to wait. Let's say the root bridge has gone bad, gone out. So the other switches are still following that, whatever the rules are, the way they communicate. But after waiting for 20 seconds, if they do not hear anything from the root bridge, they will try to have another spanning tree. They will run another algorithm, and somebody else will become the root bridge. No, but the problem is once somebody else becomes the root bridge, you can see that it is not instantaneous. It's not right away. So what happens is, as I said earlier, there are 5 stages. Blocking, they will all go in a blocking state. Everything is going to be blocked. Then they are going to go, and next stage after blocking is they are going to go and listen it, learn it. They are going to go learn it. And when they learn it, after that, they are going to listen. Because remember, learning process is by listening. So you listen, then you learn. So blocking, listening, learning, and then forwarding. So that means if you look into the span, for 20 seconds they are waiting, then then they are going to listen for 15 seconds, and then from 15 seconds listening to learning another 15 seconds. So 30 plus 20 means 50 seconds, and then they move into forwarding states. So that means 50 seconds is eternity in your communication world. So just imagine 500 computers, your switch has gone in blocking state. That's how it goes. Remember that in 2000, I think 2005, remember there was the electricity problem areas? Exactly, this is, they went into the loop, cascading thing happened, and everything went into the blocking state. So no light, no current in Canada and most of the North America part. But they take 50 seconds. Something goes wrong, they re-elect another switch to become a root bridge, so everything has to be stopped. Okay, let's see the next part. So one machine has become the root. How do we know? They will show you this. They are in forwarding states, and what are their roles? Their roles are called designated roles. They are designated to forward things. What is the cost? Cost depends upon your topology. Because I am using fast Ethernet, so by default, if you are using 100 megabits per second, the cost to send something is 90. If you are running gigabits per second, you will see that the cost is 4. If you are running 10 gigabits per second, then the cost is 2. So smaller the better. Now the second thing is, how do this is our main next question, how do they fix on the root port? Because every other switch has to talk to the root switch or root bridge, what we call. So they are, because this switch, both of them have two ports. So which port is going to go and become the root port? Only one of the root port of every switch is going to become the root port. Remember that. Otherwise, they may go in a loop. So traditionally, the first thing is, this is a rule algorithm, that port is going to become a root port, which has the shortest path to talk to the root bridge. And that shortest path is based on the cost. And the cost here is, as I said earlier, we have seen 19 because the Ethernet 100 megabits per second. So cost from here to here is 19. Now, how do they know? Because this root bridge, when it's sending BPDUs, it is sending it with the cost 0. So cost 0 here, cost 0, because it started at the initial point. This is from where it starts. So it says, if to reach to my port F01, cost is 0. To this side, it says, because it's just sending it, cost is 19. Cost is 0. Cost is 0. When it comes to the other switches, on which interface they are listening, they are adding their own ports bandwidth. Like we are having 100 megabits per second. So say, oh, so its cost here is, I have to pay 100. Oh, sorry, 19, because the cost is 19. So 19 will be cost here. 19 is going to be cost on this side. 19 will be cost on this side, because I'm using all fast Ethernet. So port number F2, this port becomes the root port. Similarly, on your switch number 2, one of the port becomes the root port. So that they are going to go and talk, you can see there. So F02 here becomes the root port. F02 from here becomes the root port. And all these ports here are all called designated ports. They are all in forwarding state. So this is forwarding. Okay, you can see this one. This is going to forward, so I'm just putting, we call it a designated port. That means they are sending it. You are designating those ports to forward. Yes, these two. Then this port here is a root port, because it's going to go and talk to the root bridge. And this port is one of them. We will see that which one is going to be a root port, so they can talk to the. Okay. Oh, come on. So this is DP, this is DP. That means forwarding state, forwarding state. RP means every switch which is not a root bridge will have a single root port. Single root port. So it is going to go send it here, it's going to send it to the root. Okay. So this guy is sending them the BPDUs. Nobody else is sending it. Once it is decided that this guy is the root bridge, the all others are not sending the BPDUs. They are just updating. Okay. Next one is now the call designate port. Because what about this? You can see that this is one port here, only one is used here, only one is used. Now there are two ports here. We are connecting here. So third rule is that after fixing root port, after fixing root bridge, for every broadcasting domain or every segment, you must have a forwarding state. So you must have a forwarding state. Otherwise, if you put computers on this side, they won't be able to talk. So designated port means then from this to this, they are going to go and figure out which one is going to become the designated port. Note, so again, number one, the rule here is, the first thing is they always go and check the bridge ID, MAC address. So you can see there in these three, one is, if you look into that, this is O00D0, this is 5822D and blah, blah, blah. and then S3 as this one. So whichever is going to go and have a smaller ID, comparing this one and this one, not the root bridge, because root bridge is gone. We are only comparing between these two. 3 is already root bridge, okay? So one of them becomes this is designated port, and the other one here goes in a blocking state. So you can see now. You can see there, this one is in a blocking state. This port, this. So that means message comes here, it goes here, it cannot go this way. So what we are learning here is that when we are working on a redundancy, when we want to go protect our network in case one of the switches or n-1 of the switches goes bad, still we have the connectivity. The problem here is because we are not using any logical concept. There's no IP, there's no name. Everything is a broadcast because the message comes in, they broadcast. Either the broadcast or the filter, if they know where to send it. And they always learn, the switches always learn the MAC addresses by the source address. Remember the rule. So when you are learning by the source address, you will never ever learn, a switch never learns the broadcast address source, because broadcast address is all 255, all Fs. It will never learn the multicast. It will never learn the Unix broadcast. So you have to have some MAC address in your MAC address table. Only then you can go and forward it. Otherwise, broadcast. So remember the principle again. If we have one switch, we don't have redundancy problem. That is like a king, one man king, one person. But the moment you are going to go and put more than one switch, and then you go and connect them, you are going to have trouble. So for example, another algorithm maybe, so something goes wrong here, then other machine becomes a root bridge. But again, every network which is having more switches must have a root bridge, number one. So all the ports on the root bridge are sending. Number two, every other switch which is not a root bridge must have a single root port so that they can talk to the root bridge. And the criteria of becoming a root port is what? Lowest cost. If the cost is same, then they go and check the bridge ID. So for example, if you have path, you have 2, 3, 4, 5 paths, and all of them have the same cost, X. So then which one? So then the system is going to go and compare the bridge ID. And what is the bridge ID? As I told you earlier, this is your bridge ID, 32768. It is a multiple of 4096. Because this 12 bits means, if you go math, do a little math, 2 to the power 12 is 4096. So 2 to the power 12, 4096 means when we are increasing or decreasing as administrator, we can go and make changes. So if you want to make any other bridge a root bridge, it's up to you. So what you do is, we go to the bridge and we run a command, and we want to, for example, here I have a command here, spanning tree VLAN 1 root primary. So for example, if you want to make, I just want to show you one of these. Let's say I want to make this a root bridge. I don't rely on the system. Reason it is because maybe this is my important building's route of the switch. So what I do is, I can go and write a command. I have to be on a global mode. And while I'm in a global mode, I will run this command, spanning tree. This is the easiest one. VLAN, you make sure that you are in which VLAN. Reason is simple because, as I said earlier, Cisco is having a spanning tree instance for every VLAN. So VLAN 1, because traditionally we don't have another VLAN. And we say root. And I want to make this machine a primary. Oh, there has to be a space, VLAN space 1. Now once I've done it, let me go and show you what is happening at the background. So if I say show spanning tree, you can see it is listening. You can see that means the process is redoing everything, reprocessing. And now you can see that once you make one of these as a root bridge, because I made it as a root, I wanted this switch to become a root. So priority has become 24577 plus, because in VLAN 1, so your bridge ID is 24577 plus 1. You can see this one. So 24576 plus 1 becomes 24576. This, because this is always a multiple of 1496. Reason this 12 bits. This. So what we are doing is 4 bits, we are changing it. This is a multiple of 496. You can type 496, you can make anything which is a multiple of 4096. For example, 04096, then multiply 4096 with 2 and then keep doing it until it goes up to 60, 61 something something. But if you have redundancy, you make sure every one of the switches has to be a root bridge. Every port, you can see now I made S2, so you can see now all these ports are in a forwarding state now. So this is no more root port, is gone. This is gone because we have reconfigured everything. This is gone. And this is gone. But they are going to go recalculate everything again. So how do I know that? Let's go and check on the switch to which I made. You can see every port is in designated port. And number 2, spanning tree enabled protocol, we create IEEE. So IEEE is basically 802.1d. 802.1d. Priority is 245676 plus 1. That's why it makes 7. This is the address of this machine. You can see this computer server 2 has become the root now. This ID. Everything else is the same, but every port has become a designated port. Let's go and check this machine. It has to have a root port. Remember I told you every switch must have a root port. And the root port is, how do we configure? We configure by lowest priority. If the priority is same, then with the lowest bit. Bit means bridge ID, number. 32768 or whatever that number is. So show spanning tree. So you can see now this machine has 3 ports. On one you have a computer. So on one you have a computer that has to be designated port. But the other port which we are connecting with the switches, one is root port and the other is in a blocking state. One has to go. So the state is blocking, but the role is, we call it alternative. That means in case something goes wrong, right away the system is going to go and shift this one, move it to forwarding state. So you don't have to wait for the 50 seconds. And now if you go to this switch 3, you can see that. So show spanning tree. So it says, oh, root IDs, that guy has become the new root 24577. This bridge ID, that means this machine is not a root bridge because this bridge ID, you can see this one. Priority is this number. And these two are different MAC addresses. You can see this one and this one. So that's why it cannot be a root bridge. The system IDs, again, as I said, bridge ID is always equal to priority, which is by default 32768 plus the number of the VLAN, because this everything is VLAN 1 right now. That's why this number is 32769. And then these are this switch is having 2 ports. One of the port is a root port, and the other port is a designated port. So clearly that means to break the loop, you can see that the traffic moves here. From here, it goes to this, it comes up here, then when it goes here, this machine is not going to be sending it out. Nothing. It is just listening, but it's not sending anything out. So you have broken the loop. Otherwise, if you don't do it, then you have no control because they keep on forwarding. You learn some address A here, then I send to you, you learn that address A here, then you go send it here, then again you learn send that address A again. So problem here is if you don't have a spanning tree, you may be, we call it, the term is known as flapping. Flapping means you are updating every time a different source address. Because one time you are listening from here, next time you are learning from here, third time you are learning from here because you are in loop. So spanning tree algorithm by default is one of the objectives of using the switches. So again, let me finish it before I leave. When you have redundancy, you have more than one switch in your network. By default, system is running spanning tree algorithm. So this algorithm is by default running. And what is the standard 802.1d? The Cisco calls it a PVC, per VLAN, per VLAN. That means because in 802.1d, they say one spanning tree for the whole network. Whereas Cisco says no, because you may have more than one VLAN. So what they are trying to do is they are going to go and give you different spanning trees per VLAN. So per VLAN spanning tree. So what we call P per VLAN as spanning tree. So IEEE, but when you link here, when you click on this, and then you can see say IEEE. So IEEE basically means is from the standard which we say 802.1d. But if I type a command show run here, I will show you. Cisco says, well, they do use this one, but they hide it. They say, no, we are using PVST. Spanning tree mode is PVST. That means per VLAN spanning tree. Because right now we have only one VLAN. So we have only one instance of this the whole concept. So this was the lecture which I wanted to give you, but there are more coming up on spanning tree because we are going to go and talk a little more about this one, that how do we change these things, how we change the priorities and all that. As I said earlier, I want to make this one the primary, the root, or I want to go become a secondary. We are going to go and look into that. So keep subscribing to my site and keep doing these labs, keep learning it. This is very, very important because switching is a very important part of your CCNA exam. So you have to know each and everything, and they do ask all these questions which I am discussing. So then until next time, keep doing it, keep reading it, and then keep subscribing my channel. Thanks and have a good day, and hopefully you enjoyed my lecture. Okay, bye.